In this video, we will describe what happens in the modulation and demodulation part of an AM radio system. Now, AM radio may seem like so last century to most of you. In fact, there aren't that many stations that still do AM radio as their primary mode of operation. But it turns out that the concepts in terms of what's happening in the frequency domain actually are still fairly valid, in the sense that the specific modulation technique has changed, but there's a lot of similarity between modern digital systems and the AM radio in terms of how they operate in the frequency domain. So what I have on the screen here is a diagram of an AM radio system. And the idea is that we have a microphone that collects, say, speech signals or something like that. And the output of this microphone goes through an AM modulator. And the output of the modulator is the signal that's going to be broadcast. So this signal gets sent up into the antenna, somewhere up here. And then that signal is broadcast by the antenna to, let's see, what's a good color for electromagnetic radiation? Here we go. To the antenna of this radio. And so the idea is that the radio now wants to take the signal that's been broadcast and get the speech signal back so that you can listen to talk radio or whatever it is you're listening to. But the problem is that other radio stations are also broadcasting signals, and these other signals are also showing up at the antenna. And so the tricky bit is how the AM radio is going to select the signal we want from all of these other signals that are showing up. And that's the purpose of AM modulation and demodulation. It allows us to do that. And it turns out that analysis of this system really works best in the frequency domain because in the frequency domain you can see all the different things that are happening in the modulator, and then you can see what happens in the radio receiver as well. So let's bring up an empty window and we'll look more carefully at what happens inside the AM modulator. So this is our AM modulator again. And we have our signal coming in. And the first thing that happens inside the AM modulator, we'll call our signal coming in M of t, is that we add 1 to it. And the idea is that we want to raise the M so that it doesn't go negative. So we'll make the assumption that the absolute value of M is less than 1. So the idea is if I have an M of t that maybe looks something like this over some short period of time, after I add 1 to it, that just raises it up by 1, so I get basically the same thing, but now it doesn't go below the axis. It never goes negative. After we do this, then we multiply by a signal which is cosine omega c t. Omega c here is called the carrier frequency. And this is the output then of our modulator. We'll call this x of t. And this is the signal that gets sent through a very large power amplifier and then broadcast through on the antenna. If you look at what x of t looks like in the time domain, it basically has the envelope given by the previous signal. So I'll draw that envelope. But then it wiggles between the two ends of this envelope at a frequency that is omega CT. And so you can see that the amplitude of the cosine waveform is now dependent on my m of t that was put in. That's why it's called amplitude modulation. Okay, now many of you are probably thinking that I've already lied to you. I said we were going to analyze this in the frequency domain because it makes the most sense. Let's go back and look what happens in the frequency domain as I run m of t through the AM modulator to get x of t. So in the frequency domain, let's look at the magnitude spectrum of m of omega, which is the Fourier transform of m of t. And we don't know exactly what it is, but we will assume, for the sake of this presentation, that it has been low-pass filtered so that it fits between 2 pi times 5 kilohertz and minus 2 pi times 5 kilohertz. In other words, it has a bandwidth of 5 kilohertz. And the reason we do this is that that's the way AM radio actually works. Although I can't remember if it has a bandwidth of 5 kilohertz or 10 kilohertz. But in any case, it has a very limited bandwidth. And we will use this fact that it has a limited bandwidth to allow this signal plus many other radio stations that generate other signals to exist in the same frequency band. Or I'm sorry, to exist in the same electromagnetic spectrum in such a way that the radio can pick out the station you want. So this is what we have here. When we add 1, then essentially all we add is a delta function at the origin of magnitude 1. Okay, so by adding 1, I've just added this delta function. And now the magic occurs. Here, we'll do this in a really magical color. When I multiply by cosine omega CT, I'm multiplying in the time domain, which means that in the frequency domain I'm convolving m of omega with the Fourier transform of cosine omega CT. And you'll remember that the cosine of omega CT has a Fourier transform that looks something like this. And when I take my m of omega and convolve it with these delta functions at minus omega c and omega c, I basically get 2 copies of my m of omega plus this delta function at 0. But each copy is shifted by omega c, in this case, because I have the delta function out here, or by minus omega c, because I have this delta function out here. So again, what's happened is I've taken 2 copies of the spectrum. One goes out here, and the other goes out here. Okay, so this is oftentimes called the modulation property of the Fourier transform. It turns out, again, it's sort of the fundamental thing that happens or that gets used in almost every communication system on the planet. So just to make it clear, this is the magnitude spectrum of x of omega. Now, one of the things I'm not doing here is I am not looking at the phase of these spectra. And so the cosine omega CT, as I've got it plotted here, actually is okay. But it turns out that you can get yourself into trouble if you forget that these Fourier transforms also have a phase spectrum as well as a magnitude spectrum. So the last thing to point out before it looks like it's time to end this video, and then we'll talk about the demodulator in the next video. This spectrum fits between omega c minus 2 pi 5 kilohertz and omega c plus this same amount. Okay, so I've taken this signal, or the spectrum of m of omega, and I've moved it up to the carrier frequency omega c. So with that, we'll end this video, and in the next video we'll talk about how to do what the demodulator does and how it works its magic to reconstruct the signal.